Hi, it's Big Tuition, and it's time for a quick review of the chapter of integration. So for integration, the simplest way to think about it is the reverse of differentiation. It's a bit like the inverse functions that we've studied earlier in functions. But essentially, it's like reversing the effect of differentiation. Instead of finding the rate of change, we are thinking of the cumulative effect. Cumulative effect, yes. And this is often represented as an area under the graph. Yep, so the common integrals not in MF26 are given by this. This is the common integrals not in MS26 is given by this. And you will notice that these are actually very similar to the derivatives that we discussed for the chapter of differentiation. So we notice that, like, for example, the first one, when we try and integrate a polynomial term, x to the power of n term, we see that actually this is like we're trying to reverse from here to here, right? So n to the power of minus 1, when we try and reverse it, the n will be the power of n minus 1 becomes n. Like here, the power of n becomes n plus 1. Then you must divide by n to remove it. Here, you divide by n plus 1. So actually, integration and differentiation is very closely tied together because the derivatives is basically the same as the integrals, except you just need to flip the notation and make sure you add the plus c. Okay? So other similarities you can see is we differentiate sine to get cosine, but then we integrate cosine to get back sine. We differentiate cosine to get minus sine, we integrate sine to get minus cosine, so on and so forth. Okay? So just study one of these pairs by heart, either the derivatives or the integrals, and essentially it's like buy one get one free, right? So next is a technique for integration called integration by parts. So by parts just means you integrate part by part in a sense. So you may think this is very intimidating to remember, this equation, but actually this is just a representation, a different way to write the product rule. Okay, so when we write it this way, we can integrate both sides. We integrate duv dx, we can use this integral to tell us that integrate duv dx with respect to x is this just gives us uv. When we integrate this whole thing with dx, we get integrate u dv dx plus integrate v du dx. You can't really simplify this further. You can distribute the integral. You can distribute the two terms, this term and this term, into two separate integrals, but you cannot simplify it further. Then we can rearrange it. We can rearrange, integrate dv du, this term go here, dx, equals to uv, this term goes here, minus, because we are shifting the term from one side to another, integrate v du dx, like this. Okay, essentially integration by parts is the integral form of the product rule. Okay, so integrating expression with two or more different types of function will be useful. Integrating by parts will be useful for integrating expressions with two or more different types of functions. Because when we have two or more different types of functions, it's not immediately obvious how we can go about integrating them. So for example, like x sine x is not so straightforward, right? So yeah, we can't just differentiate, or we can't just integrate this. So when we have integration by parts, however, we can differentiate this. When we try and integrate x sine x dx, we have to choose one of this to be u or dv. it's not immediately straightforward that x is u or sine x is dv dx, okay? So how do we choose which one to be u and which one to be dv dx? We follow the latte rule, which tells us which is the better u to choose. So the reason why it is there's this order is just because when we do integration by parts, we notice that we are basically trying to differentiate the u and integrate the dv dx. When this happens, we are hoping that we get a term here that is more easily integrable. As such, when we choose the u in this order, we will end up with most of the time, with a more easily integrable function. So let's try this example. We see that the u has a priority of logs, logarithms, inverse trigonometry, algebraic, trigonometry, and exponentials. So here the first one in this priority list will be algebraic. So we set u equals to x. Du dx is then 1. dv dx is sine x. V is, we can use this, and we see that V is minus cosine. Okay, V will be minus cosine. Here we can drop the constants first because we can add, all the constants can just merge to become one total constant at the end. So we can see that this equals to uv, which is minus cosine x, minus integrate v du dx. V is minus cosine x dx. Du dx is 1, so it's just dx. And this is minus cosine x plus integrate cosine x. Okay, yeah, let me tidy this up a bit. Moving on, we can see that this is minus cosine x plus integrate cosine x give us sine x. So this will give us sine x. And of course here we can write a plus c to indicate the total constant of integration. So here, here it is x. Here there should be a minus x, yeah, it's a x instead of a minus x, minus. And our final answer is therefore minus x cosine x plus sine x. Plus c. Okay, so this is how you do integration by parts. Sometimes it is not immediately straightforward about that. You may not necessarily get a nice term like this. So one example I could immediately think of, it would be maybe something like e to the power of x. E to the power of x will be more complicated, where here your u will be sine x, du dx it will be cosine x, your v dv dx is e to the power of x, and your v is e to the power of x, right? So in this case, your integration by parts will be equals to uv e to the power of x sine x minus v du dx, which is ex. dv dx is, ex is v. du dx is cosine. And we notice that we actually end up with a very similar term as the original expression. So actually what you do now is try it, okay? Try it. I'm not going to do it, but try it. You do integration by parts again, and you will end up with a term that says e to the power of x sine x dx. So your left hand side has ex, integrate ex sine x. Your right hand side have an integrate ex sine x. You can group the two together, then you have 2 ex sine x. The signs will add up lah. In this case, they'll add up. Try it, okay? And then you just need to divide by 2. then your right hand side is your answer. Okay, try this exercise. Moving on, partial fraction decomposition. So sometimes we have to integrate a polynomial fraction in the form of px over qx. So this px over qx may be quite complicated. There might be multiple factors in there. So for example, the denominator qx might actually be a factor like this, ax to the power of n. Okay, so to do this, we need to do partial fraction decomposition. So partial fraction decomposition is strictly not in the chapter of integration per se, but I'll just briefly do a simple example to show how this can help. So for x, let's say 4x plus 1 over x plus 1, x minus 2 equals to a x plus 1 plus b x minus 2. Okay, to do a partial fraction decomposition, the reason why I write a x plus 1 plus b is because these two will be constants. Okay, how do we know these two are constant? Because the denominator has a maximum power of 1, and the numerator will have 1 power less. So if let's say the denominator is something like x squared plus 2, then the numerator you have to write ax plus b. Okay, just a thing to take note. But in essence, once you write this step out, the rest is just a simultaneous equation. So we can multiply the denominator on both sides. So 4x plus 1 equals to a x minus 2. Why is there no x plus 1? Because it cancels with the denominator over here when you multiply the whole thing to the right hand side. Then we can plus b x plus 1. Same thing, the x minus 2 is cancelled out with the original denominator over here. So now we can just choose two arbitrary values of x. Because this is an equation, so any values of x would satisfy this equation. We can just choose any two values of x, two equation, two unknown, we can solve the equation, simultaneous equation. Okay, but for making things simpler, we can choose the x smartly. So here we see that when x minus 2, right, is 0, our a disappears. So we choose x equals to 2. X equals to 2 so that x minus 2 equals 0, right? So x equals 2, we get 9 equals to a 2 minus 2, this whole thing becomes 0, plus b 2 plus 1 is 3. So b is equals to 3. We can also choose, we notice that when x is minus 1, x plus 1 is 0. So then b will disappear. So we try x equals to minus 1. Then 4x plus 1 will be minus 3 equals to a minus 1 minus 3 plus b minus 1 plus 1. This will become 0. As such, we get a equals to 1. And so we can substitute these values in. So then this will become 1 and this will become 3. And when we get to this stage, this is much easier to integrate because we know that this is basically this integral. Wait. Oh, it's not here. Okay. It's basically integrate 1 over x dx equals to ln x. Okay? It's basically this integral. I think this is in the MF26. That's why it's not here. Okay, so in any case, please remember this also lah. It's useful. Okay, so moving on, we have definite integrals. Definite integrals is actually more visual because previously it's all like equations and stuff, but definite integral we actually get to see graphs. In this case, definite integrals is like trying to find the area of a graph within an interval. It is represented in this form over here, okay? In this form. So when we write the integral, we say we integrate from a to b, the function. We integrate the function from a to b with respect to x. So what it means is, if let's say in this graph fx, right, and this is a, this is b, we are actually looking for the area under this graph, which is shaded lah. So it is equal to fb minus fa. So we just need to take the integral. Here you notice there's no constant of integration. Why? Because when we integrate, we have fb Oh, FB is the integral. After we integrate the integral, we substitute the a and b in. Okay, so we notice there's no constant of integral, no c, no plus c. Because FB, we have to plus c. FA, we have to plus c also, but then there's a bracket. So plus c minus c, you just, the constant of integration just cancel out. Therefore, we don't need to consider the constant of integration anymore for definite integrals. Okay, so one way to think about what this integration mean, right, is that we can think of this integral as a sum, and fx as a height, and dx as a width. Okay, why do I say these are height and width? We look at here. We want to find the area under the graph, right? So if we treat dx as a width and fx as the height, we are essentially finding the area of this block, or as I would like to call it, the area of this slice. And when we sum it up, when we sum up all the small slices, right? When we sum up all the small slices, we actually get the area under the graph. So in a sense, you can think of this dx as the width that you are summing over and fx as the function you are summing over. And then when you integrate them this way, you get the area under the graph. Okay? The fact that when you think about it, when you think about integration as summing up slices, this helps a lot when it comes to other application of integration, such as finding volumes of revolution. So suppose we want to find the volume of revolution of a funny curve that looks maybe like this. Okay, maybe something like this. So the volume of revolution will look like this, with another, okay, no. So the volume of revolution will look something like this. And to find this volume, we can think of it as slices. So this is a pie. This is like a single block of cylinder. And we can cut out one slice like this. This one slice has a width of dx. If this is the x-axis, this has a width of dx. And the radius of fx. So what's this volume of this one block? The volume of this one slice, right, is f x whole thing squared times pi. This is pi r squared, right? Pi r squared is the area of the circle times dx. Dx is the thickness of this slice. So when we write it as pi r squared dx, this tells us the volume of this small slice. Then we just need to integrate. From, let's say this is a, let's say this is b. Then we need to integrate from a to b. Pi fx squared dx. And this tells us the volume of this entire volume of revolution. So thinking of it as a slice actually really helps. Yeah, I hope this was useful. Now we move on to differential equation. Okay, so differential equation is actually the culmination of all your calculus that we learned so far. Differentiation, integration, and everything. Mostly integration actually. So differential equation is about an equation involving derivatives. So we are saying that now we have, instead of just x equals to y, we have the rate of change equals to something. And we want to solve what's the y. The most straightforward differential equation is actually simply just this type. Just like, oh, dy dx equals to this function. Then what's your y? Then your y is just integrate fx, right? Okay, this just reverse your differentiation. So this is the simplest type of differential equation that you will encounter. It's actually basically integration. So there are other types which involves. Okay, before we move on to other type, I'll briefly talk about a practical example involving derivatives. So one practical example involving derivatives could be a spread of COVID-19 virus. So if let's say you have a population of infected people. So let's say P is the number of people who are infected per day. no, P is the total infected population. dP dt will be the rate of change of this infected population. So this is, dP dt is basically like how fast people are getting infected. And this will be related to a factor of, to a linear relation, to a is proportional to how many people are infected, right? So maybe this will be dP. So this will be dP dt equals to kp. Remember, P is the infected population. So then we want to know how does this grow. Then we need to solve for P. And this is why we need to learn differential equations. Okay? So the most straightforward type is just a simple integration. The second one is what we call a separable differential equation. What we mean by separable is that now we see that we can basically group all the x terms together into a function multiplied by all the y terms that are grouped together in another function, and they are multiplied. What happened is we can now basically dy dx 1 over gy equals to fx. Then we can integrate both sides with respect to their own variables. So the left hand side we integrate with respect to dy, and the right hand side we integrate with respect to dx.